Good day, everyone. My name is Farhan Amanulah Iryadi, and I'm presenting this research alongside my colleague, Rafino Yudhistira. This work was conducted under the supervision of our lecturer. The first one is Miss Kristien Margi Suryaningrum, S.Kom M.Cs, and Mr. Panji Arisaputra, S.Kom M.Kom. This work, and we are honored to share our findings with you today. So, for the introduction phase is going to be explained by my colleague Rafino.
So, the introduction. Driver inattention caused by drowsiness and distraction remains a critical issue, contributing significantly to road accidents and fatalities worldwide. In 2022 alone, over 42,000 lives were lost on US roadways, with more than 3,300 deaths directly linked to drowsiness and distraction. To address this issue, our research investigates how advanced machine learning models can improve driver monitoring systems. Specifically, we compare two models, Faster RCNN and YOLO V10, to evaluate their effectiveness in detecting driver drowsiness and distraction using facial landmarks. We aim to identify the strengths and weakness of each model and provide insights into their potential application in enhancing road safety. For our objective, the objective of this research is to evaluate and compare the performance of two machine learning models, FastRCNN and YOLOv10, in recognizing driver states, specifically drowsiness and distraction. This involves analyzing their performance based on key metrics such as accuracy, precision, recall, and mean average precision. Additionally, the study aims to determine the trade-offs between these models and assess their feasibility for real-time driver monitoring systems. Now the methodology will be explained by my colleague.
So the methodology that we used for this research was conducted in 5 structured stages. The first one is tools and utility preparation. The first step involves setting up the development environment with the necessary tools for image processing, model training, and evaluation. The next step is data collection. A dataset comprising images of drivers in 3 states, awake, drowsy, and distracted, was gathered. The diversity of the dataset ensured that the models could be trained for real-world scenarios. The next step is data preprocessing and splitting. The data was carefully preprocessed to ensure accurate labeling and efficient usage during training. Then it was divided into training and testing subsets. The next step is the modeling. Both YOLO V10 and Faster RCNN models were trained using this dataset, focusing on detecting driver states based on facial landmarks. Each model was optimized for performance and accuracy. The last step is model evaluation. Finally, the models were evaluated using 4 key metrics. As mentioned before, the first one is F1 score to measure the balance between precision and recall. Precision. The second one is precision to assess the accuracy of predictions. The third one is recall to evaluate the ability to capture true positives. And lastly, mean average precision or MAP to assess object localization accuracy. These steps allowed us to systematically compare the capabilities of both models. And the results, the evaluation revealed significant differences between YOLOv10 and PasterCNN, where for F1 score metric, YOLOv10 achieved an F1 score of 70%, indicating a strong balance between precision and recall. Meanwhile, PasterCNN on the other hand recorded a lower score of 57%, suggesting a less consistency in its prediction. Precision, however, YOLOv10 demonstrated higher precision, scoring 71%, which reflects its ability to accurately identify driver states like distraction, or drowsiness. Faster RCNN, however, achieved a precision of 58% with more frequent false positives. Third metrics is recall. YOLOv10 also performed better in recall with a score of 70%, effectively detecting most true positive cases, while Faster RCNN's recall was lower at 56%, indicating limitations in identifying true positives. And lastly, MAP. Finally, YOLOv10 outperformed Faster RCNN in mean average precision, scoring nearly 60%. This shows YOLOv10's superior ability to localize and detect driver states, even in challenging conditions. In contrast, Faster RCNN scored only 38%. These results highlights YOLOv10's consistent performance across all metrics, making it more suitable for real-time applications. And lastly, for the conclusion, Our research demonstrates that YOLO V10 outperforms Pastor in detecting driver drowsiness and distractions. Its higher accuracy recall its higher accuracy, recall, and processing efficiency make it a better candidate for real-world driver monitoring system. However, faster RCNN remains valuable in environments where high sensitivity is required. Looking ahead, combining the strengths of both models could pave the way for even more advanced monitoring systems capable of improving road safety and reducing accidents. We hope that our findings contribute to our further innovation in this critical field.
So, thank you for your time and attention. We appreciate the opportunity to share our research with you and welcome any questions or feedbacks you have. Together, we can explore how machine learning can contribute to safer roads for everyone. Thank you.